Good afternoon, class, and welcome to Chapter 8, Part 2. As always, please have your periodic table, pen, pencil, calculator, and the pre-printed notes. Okay, so we're going to continue talking about gas laws. The next law that we're going to talk about is the combined gas law. The combined gas law is exactly what it sounds like. It takes the relationships from Boyle's law, Charles' law, and Gay-Lussac's law and combines them into one big law. And that combined law says that P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. Okay, let's try some problems with our new gas law. Example 7. If a gas has a volume of 675 milliliters at 35 degrees Celsius and 646 millimeters of pressure, what would the new volume be in milliliters of the gas at negative 95 degrees Celsius and a pressure of 802 millimeters of mercury? So we have some information here. We have a volume and a temperature and a pressure. We are looking for a new volume, and we have a secondary temperature and a secondary pressure. So we are going to use the combined gas law to solve for our missing volume. Before we get started, remember that we want to put our temperatures in degrees Kelvin because we always use degrees Kelvin. So we have 35 degrees Celsius. Hopefully you will remember from previous lessons that in order to get to Kelvin, you need to add 273 degrees to your temperature in degrees Celsius. So 35 plus 273 gives us a new temperature of 308 degrees Kelvin. So our T1 is equal to 308 Kelvin. Our V1 is equal to 675 milliliters. And our pressure, our P1, is equal to 646 millimeters of mercury. Our second temperature, our T2, is negative 95 degrees Celsius. So typing into our calculator, negative 95 plus 273 gives us a secondary temperature of 178 degrees Kelvin. Okay, 178 Kelvin. And let's see here, we have a new pressure of 802 millimeters of mercury. So again, putting this into our equation, we have 646, right, that's P1, times V1, which is 675 milliliters, divided by T1, which is 308, equals our P2 is 802. We don't know V2, that's what we're solving for. And our T2 is 178. So with a little bit of algebra, we can solve for V2. So let's do this. Normally, I put the whole right-hand side into my calculator and get a number. So 646 times 675 divided by 308 gives us a number of 1,415.75. Then I'm going to multiply both sides by 178 to get this out of the denominator. So multiply times 178. Then I am going to divide by 802 to get that out of the way. Divide by 802. And I get a final volume of 314.2 milliliters. 314.2 milliliters. Okay. 314.2 milliliters. Let's try another one. A sample of helium gas has a volume, so we have a volume here, a V1, of 0.180 liters. A pressure of 0, so we have a pressure 1 here, 0.800 atmospheres, and a temperature of 29 degrees Celsius. What are we going to do to our temperature? We're going to turn it into Kelvin. So 29 plus 273 is 302. So we have a T1 of 308. Let me erase that real quick. Here we go. Let's try that again. 302. Okay. At what temperature will the helium have a volume? So we have a V2 of 90 milliliters and a pressure So we have a P2 of 3.20 atmospheres. And we are looking for a new temperature. So we're looking for a T2. So just like in the previous example, we have P1 times V1 divided by T1 equals P2 times V2 divided by T2. Now because the T2 is in the denominator, when you solve for that, I'm just going to draw it up here. When you have this, P1 V1 over T1 equals P2 V2 over T2. To get T2 out of the denominator, you are going to multiply both sides by T2. So you're going to move the T2 over here. Then, in order to get T2 by itself, you have to multiply both sides by T1 to get that out of the denominator. So you would end up with T2 P1 V1 equals P2 V2 T1. Then to get rid of P1 V1, you would divide both sides by P1 V1. Okay, so to solve for T2, T2 is going to equal P2 V2 T1 divided by P1 V1. Let's go ahead and plug those numbers into our calculator. P2 is 90 milliliters, so 90 times P2, let's try this one more time. P2 is 3.20 atmospheres times V2 is 90 milliliters times T1 is 302 divided by, and you're going to want to put parentheses in here, P1 is 0.800 times V1 is 0.180, end parentheses, enter key. And I get, let me see here, whoa, I did something wrong here. Did I write my numbers down wrong? 0.180, 0.80, I just got an insane temperature. Like 604,000 degrees. We did something wrong here. 3.20 atmospheres, 90 milliliters. So we increased. My goodness, I see where we went wrong. Hopefully you all see where we went wrong. We have a mixture. We have 0.180 liters and we have 90 milliliters. Do liters and milliliters cancel when you put them in the same equation? No, they do not. So the reason mathematically I came up with a mistake is because I did not convert my secondary volume into liters. Let's do that now. In order to convert milliliters to liters, we divide by 1,000. So our secondary volume is 0.090 liters. Let's try that again in our calculator. P2 was 3.20 atmospheres times V2, which is 0.090, times T1, which is 302. Now let's divide that by our P1, which is 0.800. Again, remember to use parentheses in this second part. Times V1, which is 0.180, close parentheses, enter. And I get 604. Of course, this is in Kelvin, and the question asks us for this in degrees Celsius. So to go back to Celsius, we subtract 273. And we get a final answer of 331 degrees Celsius. This is a great lesson in why it's really important to keep track of your units. As you can see, even I occasionally forget to check my units. All right, let's try the next. Okay, so our final law that we're going to talk about is Avogadros' law. Avogadros' law relates the volume and the amount of the gas, i.e. the moles of the gas. Avogadros' law is used when temperature and pressure are constant. And Avogadros' law says that V1 divided by N1 equals V2 divided by N2. Again, where N are amounts of gas, and amounts are always measured in moles. Okay? Amounts are always measured in moles. Avogadros' law, like some of the other laws we've studied, says that the volume is directly related to the number of moles. Since number of moles is essentially amount of stuff, it makes sense that the more stuff you have, the more space it takes up. The less stuff you have, the less space it takes up. So Avogadros' law is one of those nice, easy laws that really makes sense when you think about it. Now let's try an example with Avogadros' law. Example 9 says if 0.75 moles of helium gas occupies a volume of 1.5 liters, what volume will 1.2 moles occupy at the same temperature and pressure? So we have an amount. We have 0.75 moles, which is our N1, and we have a volume of 1.5 liters. Okay, we also have a secondary amount, 1.20 moles. We want to know the volume. So let's just plug this into our equation. 0.75 moles divided by, and there I go making a second mistake. Let's erase that. I almost flipped our equation over. Okay, let's try this one more time. V1 over N1. V1 is 1.5 liters. So 1.50 liters divided by 0.75 moles equals our V2, which we don't know yet, divided by our N2, which is 1.2 moles. Again, this is a fairly simple algebraic equation to solve. Typing this into our calculator, the easiest way to do this would be to type 1.50 divided by 0.75, and then multiply that resulting number by the 1.2 in order to get that out of the denominator. So times 1.2, and we get an answer of 2.4 liters, which makes sense when you think about it. We've gone from 0.75 to 1.2. We have almost doubled our number of moles. So it would make sense that they would take up almost twice as much space. Okay, let's talk about standard temperature and pressure. Like everything else in the sciences, the scientists got together at some point and decided, hey, let's pick a standard temperature and pressure at which we will all study our gases so that we can be consistent. And they came up with some values. The standard temperature for standard temperature and pressure is 0 degrees Celsius, which, since we always add 273 to get Kelvin, gives us a standard temperature of 273 K. Our standard pressure, to make things easier, was picked 1 atmosphere, also known as 760 millimeters of mercury. Why 1 atmosphere? Well, because that's what most of us experience. Now, granted, if you're high up on a mountain or you live far below sea level in a submarine, your standard pressure would probably be a little bit different. However, since most of us live generally around sea level, our typical pressures are 1 atmosphere. So that's why that was chosen. At standard and temperature, 1 mole of gas always takes up a volume of 22.4 liters, no matter what kind of gas it is. So again, let me repeat that. At standard temperature and pressure, 1 mole of a gas occupies a volume of 22.4 liters. Again, this does not matter what kind of a gas it is. They always occupy 22.4 liters. This is called its molar volume. We can use this equality as a conversion factor for gases at STP. So you can see here, 1 mole of gas occupies 22.4 liters, and 22.4 liters will contain 1 mole of gas at STP. So let's try an example problem with this. What is the volume occupied by 2.75 moles of gas at STP? So again, 1 mole occupies 22.4 liters. We've got almost 3 moles, so we're thinking that this should come out to be slightly less than 66. But let's try it. We have 2.75 moles of N2 gas. We are going to use one of those conversion factors to determine what the volume would be. We have this conversion factor and this conversion factor. Which one puts the moles on the bottom? Well, obviously it's this one, right? This one gets us the moles on the bottom. So 1 mole takes up 22.4 liters. So we have 2.75 moles. 2.75 times 22.4 tells us that 2.75 moles takes up 61.6 liters, which is pretty close to what we predicted. We said it'd be a little bit less than 66. All right, let's try another one. What is the volume at STP of 4 grams of methane gas? Okay, we have our conversion factors. We said that 1 mole occupies 22.4 liters, or 22.4 liters is 1 mole. Clearly, in order to use one of these conversion factors, we need moles or liters. We have neither. We have grams. However, using our handy-dandy periodic table, we can come up with moles, right, for any substance. So 4 grams of methane is how many moles? 1 mole of methane is 1 carbon, which is 12.01 grams per mole, plus 4 hydrogens, each one being 1.01. So 12.01 plus 1.01 times 4 gives us a total of 16.05 grams per mole. So from here we can get to grams. Now we want to get to volume, which is measured in liters. Which one of our 2 conversion factors would get rid of the moles? It looks to me like this one with the moles on the bottom. So times 1 mole over 22.4 liters. So that cancels our moles. Our grams canceled in the first step. And it leaves us with a unit of liters. So 4.00 divided by 16.05 gives us the number of moles times 22.4 gives us the number of liters. And it says that 5.58 liters is how much space 4 grams of methane gas would take up. All right, let's try one more. How many grams of helium are present in 8 liters of helium gas at STP? So now we have liters and we want to get to grams. Neither one of our 2 conversion factors has grams in it. However, they do have moles, and we can get to grams from moles. So again, let's look at our 2 conversion factors. We have this one and this one. Which one would get rid of our liters? I say this one, right? The liters are on the bottom in that one. So let's go ahead and use that one. 1 mole takes up 22.4 liters. So clearly we only have 8 liters. Clearly we're going to have less than a mole of gas. Now, how do we get from moles of gas to grams of gas, which is what the question is asking for? And again, using our periodic table, we know that 1 mole of helium gas weighs 4.00 grams. Again, this comes from the periodic table. So let's type this into our calculators. 8.00 divided by 22.4 times 4.00 gives us 1.43 grams of helium gas. Okay, I forgot about our final, really final this time, gas law. The ideal gas law combines all of the properties that we've used to study gases so far. So now we're going to combine pressure, volume, temperature, and amount, i.e. moles, into a single gas law, which is called the ideal gas law. And the ideal gas law says that PV equals nRT. PV equals nRT. If we were to rearrange this equation to solve for this new variable, which we've never seen before, right, what have we never seen before? Well, we've never seen R before, right? That's a new one. So rearranging to solve for R, we would get units of liters, atmospheres divided by moles in Kelvin. This is a very special number. It is called the gas constant. So if we rearrange the ideal gas equation, the 4 gas properties equal to a constant called R. To find the value of R at STP conditions, if we put in 1 atmosphere, 22.4 liters, 1 mole, and 273 Kelvin, we get 0.0821 liter atmosphere mole Kelvin. Liter atmosphere mole Kelvin. Now, real gases do show some deviations in behavior. They don't always equal the number we get when we plug these into the equation. However, the ideal gas law gives us a pretty good approximation of what we're looking at. Okay, we have some other values of R that we can use if our pressure is not in atmospheres. For example, if our pressure is in millimeters of mercury, our R value is 62.4 liters times millimeters of mercury divided by mole Kelvin. As always, you do not have to memorize any constants. Okay, you will have a sheet of notes with you for the final, so you can write these down. You don't have to memorize these numbers. Same thing with the equations. When working with the ideal gas law, it is always wise to make sure that the units of each variable match the units in the R you select. Otherwise, you end up like we did a couple of problems ago. The units of pressure are the only units that change in R. Volume is always measured in liters. Amounts are always measured in moles, never grams, and temperature is always measured in Kelvin. So when selecting your R, make sure that the R value that you use either matches the units of pressure that you are given in the problem, or if you're solving for pressure, make sure that R matches the units of pressure that you wish to get. It becomes important later on. Okay, let's try an example problem. Example 13, dinitrogen oxide, which is used in dentistry. It's an anesthetic that's also sometimes called laughing gas. We want to know what is the pressure in atmosphere of 3.5 moles of this stuff at 22 degrees Celsius in a 5-liter container. So we have an amount, a temperature, and a volume. Again, we have a volume, an amount, and a temperature. And R, of course, is a constant that we can look up. So we can solve for pressure using PV equals nRT. PV equals nRT. We want to solve for pressure, so we would divide both sides by volume, and we would get that pressure equals nRT over volume. So at this point, it's just a plug and chug. We have 0.350 moles. Our R, again, was selected to give us our pressure in atmospheres. So we picked the R that had atmospheres in it, right? Right here. Pick the R with atmospheres in it. Okay, so that is 0.0821 liter atmosphere over mole Kelvin. Our temperature, don't forget, we're always in Celsius, we're always in Kelvin. So add 273 to 22 and you get 295 divided by our volume, which is 5 liters. And this enables us to solve for our pressure. So 0.350 times 0.0821, oops, I missed my 1 in there, 1, times 295, then all of that divided by 5.00 liters gives us 1.70 atmospheres. 1.70 atmospheres. Okay, let's do one more that's just a little bit more complicated. Example 14 says that nitrogen gas reacts with hydrogen gas to produce ammonia gas. How many liters of NH3 could be produced at 0.93 atmospheres, which is a pressure, and 24 degrees Celsius, which is a temperature, from a 16-gram sample of nitrogen gas and excess hydrogen gas? Hopefully you all remember from a previous chapter how to determine how much ammonia gas you could get if you have a set amount of your starting products. So again, we have a set amount of nitrogen gas, but we want to know liters of ammonia. So what do? Well, we have our starting amount, which is 16 grams of nitrogen gas. As always, we're going to convert this to moles because you cannot compare grams to grams in a balanced chemical equation. Instead, you must compare moles to moles. So 1 mole of nitrogen gas weighs how many grams? Looking at our periodic table, we see that nitrogen gas weighs 14.01 grams per mole. There are 2 nitrogens in an N2 gas, so 14.01 times 2 gives us 28.02 grams per mole. That gets us moles of nitrogen gas. Now, we want to determine liters of NH3. So what do we need to do to get from moles of N2 to moles of NH3? Hopefully you're saying mole-mole ratio, mole-mole ratio. That's exactly right. For every 1 mole of nitrogen gas, For every 1 mole of N2, we get how many moles of ammonia gas? Well, according to our balanced equation, for every 1 mole of nitrogen gas, we get 2 moles of NH3. So let's cancel those out. Now we're at moles of NH3. So let's see what we have here. 16 divided by 28.02 times 2 gives us 1.14 mole of NH3. However, the question asked for liters. What do we have? We now have an N, right, an amount, which is little n. We have a pressure and a temperature. We need to solve for a volume. So let's use PV equals nRT. PV equals nRT. To solve for volume, we would divide by pressure. So volume equals nRT over P. Let's go ahead and put these numbers in. We have 1.14 mole. Which R are we going to use? Well, we have a pressure in atmospheres, so we want to use an R value that corresponds to that. We want the one with atmospheres in it. That is 0.0821 liter atmosphere mole Kelvin. And our T, we were given as 24 degrees Celsius. However, because our universal gas constant has units of temperature in Kelvin, we are going to switch those degrees Celsius into Kelvin. So 24 plus 273 gives us a temperature of 297. Divided by a pressure of 0.93 atmospheres. Took me a second to find that in the problem. And again, from here, it's just plugging numbers into your calculator. 1.14 moles times 0.0821 times 297 divided by 0.93 gives us 29.89. 29.89 liters of NH3. Most of these problems, once you know which equation to use, once you know which variables you have, are pretty straightforward. It's literally a matter of organizing your variables, determining what you have and what you're looking for. It also really helps to be very familiar with units so that you know which variables you have, because sometimes they don't tell you that, hey, this is a pressure or this is a temperature. So it helps to know that pressure is atmospheres or millimeters of mercury, that a volume might be milliliters or liters, that a temperature might be degrees Celsius or Kelvin, or sometimes, who knows, they might even be crazy and give it to you in Fahrenheit and expect you to be able to convert that to Celsius and then to Kelvin. So again, just be really careful to make sure you know what units you're dealing with. This will help you determine what equation to use when solving problems. Okay, so the last thing that we're going to talk about is partial pressure. And partial pressure is really interesting and pretty straightforward. Partial pressure of a gas is just the pressure that each gas would exert if it was by itself. So what it's saying is if you have a mixture of gases like hydrogen, nitrogen, oxygen, carbon dioxide, they don't really interact with each other. The pressure of the carbon dioxide on the walls of the container in a mixture is exactly the same as it would be if it was by itself. So Dalton's law of partial pressure says that, hey, the pressure depends on the total number of gas particles, not on the types of gas particles. And that the total pressure exerted by gases in a mixture is the sum of the partial pressure of each gas. So again, he says that the pressure depends on the total number of gas particles, not on the types. So it doesn't matter what kind of gas you have, it matters how much gas you have. So for example, at standard temperature and pressure, 1 mole of a pure gas in a volume of 22.4 liters will exert the same pressure as 1 mole of a gas mixture in 22.4 liters. So you could have a mole of nitrogen gas, a mole of hydrogen gas, you could have a mole of mixed gases, and no matter what, they will still exert the same pressure, which would be 1 atmosphere, if you were at standard temperature and pressure. The air that we breathe is a mixture of different gases, mostly nitrogen and oxygen, but contains small amounts of other gases like hydrogen, carbon monoxide, carbon dioxide. And what you and I call atmospheric pressure is actually the sum of all of the partial pressures of the gases in the air on you. In our lungs, oxygen enters the blood while carbon dioxide from the blood is released. In our tissues, oxygen enters the cells, which release carbon dioxide into the blood. In our bodies, oxygen flows into the tissues because the partial pressure of the oxygen gas is higher in the blood and lower in the tissues. And remember that concentrations always flow from higher towards lower, from higher to lower. So since the partial pressure of the oxygen is higher in the blood than it is in our tissues, the oxygen gas is willing to flow from higher to lower. Carbon dioxide flows out of our tissues and into our blood for the same reason. The partial pressure of the carbon dioxide is higher in the tissues and lower in the blood. So it's basically a constant exchange between oxygen gas and carbon dioxide, which enables us to live. This concludes Chapter 8, Part 2. Thank you very much for listening, and I hope to see you all for Chapter 9. Have a great day.